So today would be our last lecture of this semester, and we're going to finish our discussion on boundary layers, finishing it with discussion about mass transport in boundary layers. Okay, so you can see that the title for today's lecture would be Steady State Transport in Binary Boundary Layers. Okay, so let's take a look at how the equation of states should be written for a binary mixture system. So first, let's try to list that down. So basically, it's going to be very similar to those that we've introduced for non-isothermal system, except that we would have additional terms for the free convection term, the buoyant term, due to concentration gradients. And we would have an additional equation for the continuity of a particular species, but it's very analogous to the temperature or the equation of energy. So let's just write these equations of states down right now. So let's call them the extent the equations of state to binary reacting mixtures. Okay, so let's again look at the basics. So the equation of continuity would be the same altogether. We have partial Vx partial x plus partial Vy partial y equals to 0. Okay. And then we have the equation of motion, saying that we have rho times Vx partial Vx partial x plus Vy times partial Vy partial y equals to rho times VE. So again, this is already looking at what's happening in the boundary layer. So we have transformed the pressure term using the potential flow velocity. And we have the viscous terms in the boundary layer. And we're only going to be looking at the x component because that's what's more important based on order of magnitude analysis. And then we have two terms for the buoyant force. So one is for the temperature gradients. So rho g beta times T minus T infinite. And then we have another term that affects buoyant force, which is the concentration gradients. So C, or maybe we used mass fraction. So W sub A minus W sub A some infinite. Okay, so you can see that we have an additional buoyant term. But typically, they are not as important because we're usually dealing with forced convection problems where these free convection terms are not that much important. Okay, and then we have the energy equation. The energy, we have rho Cp Vx partial T partial x plus Vy partial T partial y. I think I have a typo here. Let's correct this. This should be sub x. Okay, and this equals to, so this is convective energy transport equals to the, conduction. So the thermal conductivity times the Laplacian of temperature with respect to y. And then we have chemical heat source. So let's say if there's chemical reaction, we want to include that. So it would be the, the formation enthalpy of the reactant species A over its mass minus that enthalpy for the other species B over its mass times the reaction rate. So you can see here, maybe we just write this clearer, not to confuse. So it's basically H bar. So H stands for the formation enthalpy. Okay, so basically we have a chemical heat source here. So chemical heat source. Okay, so we have the equation of continuity, equation of motion, and the equation of energy. And finally, for a binary mixture, we also need to look at the continuity of a specific species. So typically we say continuity of species A, which we have, again, on the left-hand side we have the convective mass transfer or transport. So partial W sub A partial X plus Vy times partial W sub A partial Y. And that equals to rho times the diffusion coefficient times the Laplacian of the mass fraction of A over Y squared plus the reaction part. Okay, so these are the equations of change for binary reacting mixture. And let's take a look at the common boundary conditions. So we'll call these the usual boundary conditions. Boundary conditions. So we have, first we have, let's just use the black pen. So again, we have the no slip condition. So V sub x equals to 0 on a solid surface. And we have V sub x equals to the potential flow at the outer edge of the boundary layer of the velocity boundary layer. And we typically use delta with no subscript there. And then we have the boundary conditions for temperature. So we have T equals to some T naught of x at solid surface. And it equals to some T infinite at outer edge of the thermal boundary layer. Typically we use delta sub T. Okay, and then finally we have the concentration or mass fraction. So W sub A equals to W sub A naught of x at solid surface. And equals to some infinite value at outer edge of the diffusion boundary layer. we typically use delta sub C. Okay, so you can see that for binary mixing or binary mixtures that might be reacting, we would have 3 boundary layers that might have different thickness, right? So we would have 3 boundary layers, namely the velocity, the thermal, and the diffusion boundary layer, that may each have different thicknesses. So we'll say 3 thickness, namely would be the velocity boundary layer delta, the thermal boundary layer delta sub T, and the concentration or diffusion boundary layer delta sub C. And let's take a look at, it's interesting to, do a quick analysis to see the relative thickness between different boundary layers, right? So here are some notes that maybe you want to kind of memorize at the moment, but it's easy to understand. So basically, when you're at a large Prandtl number and large Schmidt numbers, basically that's telling you that the thermal and the diffusion boundary layers are much thinner than the velocity boundary layer. Okay? But if you are at small Prandtl and Schmidt numbers, at Prandtl number smaller than 1, or let's say when, and the Schmidt number is also smaller than 1, then we have the reversed conditions. So the thermal and the diffusion boundary layers will now be thicker than the velocity boundary layer. Okay? And then also something that we want to note here is that if you're looking at mass transfer systems, sometimes the solid surface can be introducing mass to the system or at the interface, right? So let's say if you have a piece of salt that's slowly dissolving in water, then at the solid surface, you might actually have some velocity contributing in the normal direction. So putting that into a more descriptive way, that means that for mass transfer systems, the normal velocity in the y direction at the surface, meaning when y equals to 0, is usually non-zero. But really depends on the position. Okay, so we typically set v sub y equals to v naught of x at y equals to 0. And you may have cases where the net mass flux between the surface and the stream. And some examples are you might have like melting, you have drying. That's all having mass flux at the interface, right? Drying, So anything that might be related to phase change would have this kind of situation. So sublimation, combustion, okay, and maybe also you have these scenarios during transport of fluid through a porous wall. Okay. Okay, so with this said, basically, the von Karman approximation or the von Karman momentum balance will be slightly modified here. So let's just say the von Karman momentum balance now becomes what? Now becomes, you still have the same term on the left hand side, so basically this is looking at the momentum coming out from the wall and y equals to 0. Or let's say the force applied from the solid surface to the fluid equals to, the first two terms would remain the same, so d dx, integration from 0 to infinite, we have rho vx times v sub e minus vx dy. And we also have the same term d v sub e dx times the integration from 0 to infinite, rho v sub e minus v sub x dy. But we have two additional terms here, or actually three. So we also have the buoyant term, so let's put that into consideration. So 0 to infinite, rho g beta t minus t infinite dy minus the buoyant term from concentration gradients, so rho g and the coefficient times WA minus W sub A infinite dy. And finally we have the rho V naught VE, right? So the V naught here is what? V naught here is the normal component, normal velocity, or let's say net mass flux, normal to the surface at y equals 0, which we've just covered. Okay, and so this is basically, in other words, saying that this is the equation of continuity plus the equation of motion. Okay? And then we know that if we consider the equation of continuity and the equation of energy, we have the following. We have the thermal conductivity, or the net thermal or energy flux from the surface. So it's at y equals 0. Equals to d dx, integrate from 0 to infinite, rho vx times t infinite, or sorry, we need the heat capacity times t infinite minus t dy minus 0 to infinite. This is from the chemical reaction, HA over MA minus HB over MB, RA dy minus rho V naught CP times T infinite minus T naught. Okay, and finally we have the equation of continuity plus continuity of A. So we have on the left-hand side would be the net mass flux coming out from the solid surface. So partial WA, partial Y at Y equals to 0, equals to D dx rho Vx WA minus WA infinite dy plus 0 to infinite, the mass gain from reaction, minus rho V naught times WA infinite WA naught. Okay, so basically these are all the extension of the von Karman balance. So these are the extension of the von Karman balances. Okay. And they have a considerable value. In developing theory for high-speed flight for separation processes and for chemical reactions or reactors. Okay, so we've given this introduction on the boundary layer theory for steady-state transport in binary reacting mixtures. Basically, let's quickly review what's going on here. So you can see that we list down the equations of change, not equations of state, sorry. Maybe we should change this to. So equations of change. So we have the equation of continuity. The equation of motion now includes two buoyant terms. The equation of energy now includes additional term for chemical heat source, and then we introduce the equation, the continuity of A, right? So this is for mass transfer systems. Looking at the boundary conditions, again, we have Vx, so the no-slip condition on a solid surface, and the equal velocity when you're at the outer edge of the boundary layer, it should be equal to the potential flow. That's the same for temperature and concentration of mass, where you have fixed conditions at the solid surface, and you have identical condition to the what's outside of the boundary layer at the thermal boundary layer interface or the diffusion boundary layer interface. And we use delta sub T and delta sub C to represent the velocity boundary layer, the thermal boundary layer, and the concentration or diffusion boundary layer. And before going into details, we already know that if you have a large Prandtl number, if you have a large Prandtl number, then that means momentum transfer is going to be slower than energy transfer. If you have a large Schmidt number, that means momentum transfer is going to be slower than the mass transfer. So in those cases, your thermal boundary layer and your diffusion boundary layer would be much smaller than the momentum or velocity boundary layer. If the Prandtl number and Schmidt number are small, then that relation is reversed. Okay, so another thing that we want to keep in mind is that for mass transfer systems, the normal velocity at the surface are usually not zero. Okay, and it would be a function of x. That's because any system or any situation that is related to phase change, then there must going to be some net mass flux coming out from the surface. So in cases like melting, drying, sublimation, or combustion, or transport of fluid through a porous wall, in these cases, the normal velocity, or there would be a net mass transfer in the normal direction from the surface. So based on the equations of change and the boundary conditions, we can now write down the von Karman balances for velocity, for energy, and for mass by looking at the below. So if you combine the continuity with motion, then you have the von Karman momentum balance. If you combined and in the momentum balance here, again, we are introducing additional terms. 2 for buoyancy and 1 for the mass transfer outwards from the surface. Again, for the energy balance, we have additional terms for chemical reaction or chemical heat source, and additional term coming out from the surface. So if there's a mass flux, there's typically an energy flux associated with the mass flux, right? And then finally, we have the continuity of A. So we have the net mass flux coming out from the surface, or the diffusional flux, would equal to the first two terms, the reaction term, and the term coming out from the surface. So let's call this the interfacial term. Okay, so with these introduced, now let's come back to our very familiarized example looking at diffusion and chemical reaction in isothermal. So let's simplify our discussion. Let's say it's isothermal laminar flow along a soluble flat plate. So we're going to look at diffusion and chemical reaction in isothermal laminar flow. Along a soluble flat plate. And let's say in this case the Schmidt number is much greater than 1. Okay, so again, let's draw a simple schematic. So we have a flat plate right here. We have fluid coming in, and once the fluid meets the flat plate, we have the two boundary layers that's going to be developed. And because we have the assumption that the Schmidt number is much greater than 1, so we have a diffusion boundary layer and a velocity boundary layer developed, where the velocity boundary layer would be much thicker than the diffusional boundary layer. So this up here would be our velocity boundary layer. What's down here would be our diffusional boundary layer. So we would expect a velocity distribution. Something would look like this, right? So outside the boundary layer, the velocity would all be the same as the potential flow, but inside we have a curve-like shape. Okay, and so we have this. Let's use a red to kind of color code this plate. So this is a solid plate A, and we have a fluid B here. And in the description, let's say that, A is slightly soluble in B. And that means that we can say that the concentration of A, when it's infinitely far away from the surface, can be considered 0. Okay? And also, let's say if A may or may not react with B, but if A reacts with B, by an nth order homogeneous reaction. So we have RA, the reaction rate. Maybe we should use a lowercase. RA equals to negative Kn times Ca to the nth power. And also, when we say slightly soluble, that also implies that we can consider density, viscosity, and diffusion coefficient to be constant, just for the sake of simplicity. Okay, so the question is, how does the concentration profile looks like, right? So, would it look like something like this? So basically, outside the diffusion no boundary layer, you would expect that the concentration is going to be constant. But what happens inside, right? So should something happen like this, you would probably expect something also happening like a curve shape. But for simplicity, let's just say that, for our discussion, let's say that the concentration profile inside the diffusion no boundary layer is going to be linear. And because, oops, what happened? Okay. And because the diffusion no boundary layer is much thinner than the velocity boundary layer. So if you just look at the regions inside the diffusion no boundary layer, we can also assume that this part of the velocity profile as a linear within the diffusion no boundary layer. Okay, so if we make these assumptions, then we can have a fairly easy postulation of the forms of the velocity and concentration gradients. Okay, so let's continue with that discussion. So the first step is we would like to postulate forms for velocity and concentration gradients / profiles. And this is to minimize the algebra assume linear and still illustrate the method. So to illustrate the method, we are simplifying our guess to a linear profile, but in reality, we know that it might not be that linear. It might be curved. Okay, so if we consider it to be linear, then we can postulate the following, right? We can postulate that Vx over V infinite will equal to y over delta, and Vx over V infinite will equals to 1 when the y is outside the boundary layer, the velocity boundary layer, and this is when y is within the velocity boundary layer. Similarly, we can say the same for the concentration profile. So Ca over Ca naught will equal to 1 minus y over delta sub c when you're inside the diffusional boundary layer. It would equal to 0 when you're outside the diffusional boundary layer. Okay, and then let's look at our second step. So, second step, we know that the diffusional boundary layer would be smaller than the velocity boundary layer when the Schmidt number is larger than 1. So let's let the capital delta here equals to the diffusional boundary layer over the velocity boundary layer. And in this case, delta would be smaller than 1. And also we will neglect, or we can neglect, interfacial velocity. Interfacial velocity. So saying that Vy at y equals 0 due to the slightly soluble statement. Okay, so with the proper guess here, we want to what? We want to substitute these into the von Karman balance. So von Karman balance. So once we do that, the 3 substitute into von Karman balance, we now have mu v naught over delta equals to d dx times 1 over 6 times rho v infinite squared times delta. And then that's for velocity, and then for the concentration we have negative diffusion coefficient times Ca naught over delta times capital delta, which is delta sub c. This equals to d over dx times negative 6 over 1 times Ca naught v infinite delta times capital delta square minus the reaction term. So Kn Ca naught nth power and times the boundary layer thickness for the diffusional boundary over n plus 1. And from our previous statement up here, we actually know that what we know, and we have two equations, A and B. So next, step 4. From equation A, we can basically solve it the first order ODE. So from A, we know that delta, the velocity boundary layer, equals to the square root of 12 times the kinematic viscosity times x over v infinite. So step 5 would be inserting the velocity boundary layer into equation B and multiply by negative delta, capital delta, over kinematic viscosity times Ca naught. Then we get the following. We get this important differential equation, which is 1 over Schmidt number equals to 4 over 3 times x dx, capital delta to the third power plus capital delta third power plus a reaction term, dimensionless reaction term, which is kn Ca naught n power, or n minus 1 power times x over n plus 1 times v infinite times the second power of the capital delta. Okay, so basically this would be a differential equation for the capital delta. So we know that delta will depend on, the capital delta depends on 1, the Schmidt number, which equals to the kinematic viscosity over the diffusion coefficient, and 2, it depends on this bracket here, and that bracket here is actually 1 over n plus 1 times kn Ca naught n minus 1 power times x over v infinite. This is called the first Damn-Kohler number based on distance x. Okay, so the key result is already presented for you. So the key result is that there's a relation between capital delta, which describes what? Which describes the ratio between the diffusional boundary layer over the velocity boundary layer, right? And it's related with what? It's related to, it's related to the Schmidt number and also things inside this bracket, which is called the first Damn-Kohler method based on distance x. And now we're going to briefly go over 3 cases. So we're going to go over the first case, which is what if there's no reaction happening? The second case would be what happens when you're having a slow reaction or you're just very close to the entrance of the boundary layer. And the third case would be if you have a very fast reaction or if you are, very far away from the entrance at very large x. So first, let's take a look at when there's no chemical reaction. So when no reaction is occurring, that means the rate constant K sub n equals to 0. We now get the simplified equation where you have 1 over Schmidt number equals to 3 over 4 x d dx delta cube plus delta cube. And just by integration, using the integrating factors, you can get the solution. And the solution would be the capital delta cube equals to 1 over Schmidt number plus some constant over x to the 3rd quarter power. And because delta is finite as x approaches 0, or sorry, approaches, yeah, it should be approaches 0. So c would equal to 0. And so the final result is that delta is actually equal to the negative 1/3 power of the Schmidt number. And delta is going to be smaller or equal to 1. Okay, so this is something really familiar, right? This is exactly the same when we're dealing with the thermal boundary layer, right? So if you're at a case where you have a large Prandtl number, then you have your thermal boundary layer within the velocity boundary layer. In that case, we also have a very similar conclusion that the ratio between the two boundary layer thicknesses would be related to the Prandtl number to the negative 1/3 power. Okay? Now let's look at our second cases. When reaction is slow, and or when x is small. Not going into details, but basically you can basically expand the equation to a Taylor series expansion. So the end result is a series solution. Where you have delta equals to the negative 1/3 power of the Schmidt number times 1 plus coefficient A1 times C plus A2 times C to the square, and so on. Here, C equals to 12 times Kn Ca0 n power, or n minus 1 power times x over n plus 1 times V infinite. Okay, and the key here is that A1 A1 is negative 1 over 7 times Schmidt number to the 1/3 power, and A2 equals to 3 over 539 times Schmidt number to 2/3, and so on. And a key result here is that because A1 is negative, so that means the diffusional boundary layer is diminished by the chemical reaction. And this is actually quite intuitive, right? So if you don't have a chemical reaction, then the slightly dissolved species A would form your diffusional boundary layer. But if they are slowly reacted, then you can expect that your thermal boundary layer, your diffusional boundary layer would be thinner because the species A are depleted by the reaction, right? So it's kind of intuitive, but we're just showing you this in a mathematical way. And finally, for a fast reaction, or when x is very large. Not going into details, but basically it's going to be a series solution in terms of in terms of 1 over c. Okay? And for large C, we have a result that the capital delta now equals to the Schmidt number times C together and to the negative square root of it for large C. And if you expand these, you know that what? You would know that on the left-hand side, this equals to the diffusional boundary layer over the velocity boundary layer. So if you move terms here and there together, it actually tells us that the diffusional boundary layer is actually, the thickness of that is actually constant when you are at having a very fast reaction, or if you are having very, very far away from the front of this plate. Okay? And it will be independent of x, v infinite, and the kinematic viscosity. Okay, so that means that if you're a very fast reaction, or when you're very fully developed downstream, your boundary layer thickness becomes constant. Okay, so I think we have covered the boundary layer theory for momentum, for energy, and for mass transfer. And hopefully you do find these analyses useful in your own research or topics of interest. And this is going to be our last lecture for this semester. And thank you very much for your participation throughout the semester. I know that this is my first time using screenshot method to give lectures. And I'm sure that there's a lot of places that can be improved for my lectures, and if you can give me any suggestions, that would be very helpful. Maybe in the future, hopefully we can have more interactive, lectures, not like what's happening in this pandemic. But again, thank you all for your participation, and hopefully we will, people can be benefiting from this open course. So thank you.